Question 21. In a quantum mechanical treatment of the hydrogen atom, which of the following combinations of quantum numbers is not allowed? This question gives us 5 possible situations, and 4 of them are okay and 1 of them is not. So all of them start with n equals 3. When n equals 3, L can only take on certain values. L can only take on values of 0, 1, or 2. Okay, so basically the values that L can take are starting at 0, whole numbers up to n minus 1. So this actually kind of helps us right away because we can identify that E does not work because it has L equals 3. That's not an allowed value for L for n equals 3. All the other ones are okay. For each of these L values, you can have potentially multiple ML values. ML can take on values of minus L up to positive L. So if L equals 2, ML can take values of minus 2, minus 1, 0, plus 1, or plus 2. So the correct answer here is E. This question says, select the correct set of quantum numbers N, L, ML, MS for the first electron removed in the formation of a cation for titanium, Ti. So the first thing we need to do is come up with the electron configuration for titanium. And what we should do is find titanium on the periodic table, which is down here. And we go backwards to the previous noble gas, which in this example is going to be argon. So we're going to begin by writing out argon as sort of the core electron configuration for titanium, and then we're going to list the orbitals that come after. And we have these first 2 elements, potassium and calcium. Those outermost electrons are in the 4s, and there's 2 electrons there. And then we're into the 3d for scandium and titanium, and because we're 2 spots in, we're 2 electrons in, so this would be equal to 3d2. Once we've written this out, what we always have to do for our correct electron configuration is tuck the d electrons under the 4s's. So the correct electron configuration for this will be argon 3d2 4s2. First electron that will be removed if you ionize this thing is going to be the outermost electrons, or the highest energy electrons, which would be one of the 4s electrons. If it's a 4s, we know that n must be equal to 4. Because it's s, we know that L is equal to 0. Because it's L equals 0, ML can only have a possible value of 0. And then MS can be either plus 1/2 or minus 1/2. Those 2 electrons that are in that 4s, the plus 1/2 and minus 1/2 electrons, are the exact same energy, so there's no reason to expect one to be removed before the other. And so the only one that kind of corresponds to this possibility here of n equals 4, L equals 0, ML equals 0 is A, and the other ones don't make any sense. Question 23 asks for the electron configuration for copper. Now copper is an interesting one. It is what we might call a D9 metal. It's 9 spots in the D block, and the ones that are D9 and the ones that are D4 are exceptions. That's not D4. These ones are D4. So we remember these ones as being exceptions to our ordinary rules for electron configurations. So for copper, we can say that we go backwards to the previous noble gas, which is argon, and then we have 4s2 3d9. Now this one's an exception because the ones that are d9 can steal an electron from the 4s to have a full d10 shell. This is more energetically favorable. Similarly, the ones that are d4s can take 1 electron from the 4s to become d5s. So this becomes argon 4s1, 3d10. And then the last thing that we always do is tuck the D's under. So our actual electron configuration for copper is argon 3d10 4s1. That's it. 24, which of the following elements are paramagnetic? And the way you would solve something like this is to write out the electron configurations for each one of these elements. Once you've written out the electron configurations for these things, following the same steps that we just did before, you look to see which ones have electrons that are not completely paired up. So anytime you have a subshell that is completely filled, all those electrons will be perfectly paired up. So let's go ahead. We have gallium first. It has an electron configuration of core electrons argon, a full 3d10, a 4s2, and a 4p1. Now, that full 3d shell here is has all electrons paired up, so that's not going to cause it to be paramagnetic. Similarly, the 4s orbital here, if you were to draw that out like a box, you would have 2 electrons in there, they're paired up. The 4p, however, the outermost electrons, has just a single electron in there. That electron has no pair. If there's any electrons that are not paired, this becomes paramagnetic. So gallium is definitely paramagnetic. We can move to the next one, which is silicon. Silicon is also in the same row, so it's also argon 3d10, 4s2, 4p2. We can ignore this shell and this shell because they are filled. They're not going to cause it to be paramagnetic, but we look at the outermost ones, the 4p2, which would, again, if you look at those 3p orbitals, put 2 electrons in. Following Hund's rule, we put 1 in each. This has 2 electrons that are not paired. This is also paramagnetic. Next, we have beryllium. Beryllium is, that's Be, not Br. We have helium. 4s2 is the electron configuration. This s orbital has 2 electrons in it, and that has those 2 electrons paired, so this one would be diamagnetic. All right. Next we have tellurium, Te, which is krypton 4d10, 5s2, 5p4. So again, this one is full, this one is full, and we would look at the remaining partly filled p shell, subshell, in order to figure this one out. So we would look at the 3p orbitals, the 5, I guess that would be what, 5px, 5py, and 5pz. And we have 4 electrons to put in, so we use Hund's rule first. So we go 1, 2, 3, and then the 4th one will pair up the first electron, but we still have 2 that are unpaired. Therefore, this one is paramagnetic. Last one is for cadmium. Cadmium has an electron configuration of krypton 4d10, 5s2. So this has 2 subshells here that are both completely filled. All electrons here will be paired. Therefore, this one is going to be diamagnetic. Great. Next question wants the condensed electron configuration for zinc 2+. Condensed just means that we use the noble gas notation, which we've been using all along. And we're doing this for zinc 2+. For zinc, which is element number 30, we do the same as before. We go back to the previous noble gas, which is argon, and then we list out the orbitals in the order they appear. We have 4s2, 3d10. We tuck the d's under the s's, and we end up with argon 3d10, 4s2. Now this is the condensed electron configuration for zinc neutral. It wants zinc 2+. So we need to pull 2 electrons out, and the ones we pull out are the ones that are highest in energy, which are these 4s2 electrons, so that after we ionize it, we get argon 3d10, and that's it for that particular question. Question 26 asks, how many valence electrons does cobalt have? Cobalt, you can see right here. The way we do this is we go back to the first element in that row, which is potassium, and we count over. We get 1, 2, 3, 4, 5, 6, 7, 8, 9 valence electrons. That wasn't so hard. For elements that are in the D block, valence electrons are ones that are in the S and the D. For P block elements, which is sort of anything in here, these ones, the S's over on the opposite side, and the P electrons contribute to the valence electrons, not the D's. And for the S's over here, we would say S only. 26 asks, which of the following elements has the highest or greatest atomic radius? So atomic radius increases for elements as you go down the periodic table. And that's because the shells get larger as you go down the periodic table. They also increase as you go on the left of the periodic table. And the reason for this is because as you go to the left of the periodic table, the nuclear charge is getting lower, and that pulls the electrons that are in the outermost shell less effectively. And so we basically just have to identify where all of these elements are on the periodic table and arrange them based on these two simple rules that we have right here. So the one that is furthest to the left and farthest down the periodic table is rubidium. So the order goes Rb is the largest, followed by strontium, then xenon, then lithium, then neon. This is which of the following elements has the largest first ionization energy. So ionization energy increases as you go up and to the right on the periodic table. So the one of these elements that's highest up and to the right on the periodic table is chlorine. So that one is going to have the highest first ionization energy. Question 29 says to identify the element of period 2 which has the following successive ionization energies in kilojoules per mole. What we're looking for here is the point at which the ionization energies stops increasing by small amounts and suddenly dramatically increases by a large amount. And if we sometimes this is easier to spot if you have a plot. So if we draw a plot that looks like this, where this is going to be the ionization energy on the left, and this would be ionization energy 1, 2, 3, 4, 5, 6, 7, 8. And we want to plot this. Notice that the highest ionization energy in this list is around 84,000. So if we put our cap up here at maybe 100,000, We can start plotting these things. So the first one, 1314, is very, very small on our scale. It's very close to the bottom. Ionization energy 2 is a little bit higher, but not much. Ionization energy 3, same thing, a little bit higher. Ionization energy 4, a bit higher. 5 is about 10%, so we should be about up to here by the time we hit 5. 6 is a little bit higher than that. 7, all of a sudden, is very high. 7 is up here, somewhere around 70K, and then a relatively small increase to 8, up to about here. And so what we see is this kind of break in our graph where it's sort of slowly going up, then all of a sudden there's a break where it goes dramatically up, and then starts increasing again. And so what we want to do is identify where that break happens. And what we understand is that if you kind of separate these two, the ones that are easy to remove are the valence electrons, and the ones that are difficult to remove are the core. So what this graph tells us and what this table tells us is that we're dealing with an element here that has 6 valence electrons, and once you've pulled out all 6 of those, you're digging into the core at that point, and that takes a lot more energy to remove those ones. So what element in period 2 has 6 valence electrons? That turns out to be oxygen. Okay. Question 30. Elements with what first ionization energies and what electron gain energies generally form cations? So for something to form cations, you need to have a low first ionization energy, because that makes it easy to remove that electron and generate that cation in the first place. So things with low ionization energies lose electrons easily, become cations easily, generally form cations. The second one is blank electron gain energies, and this one should be more positive, which I think corresponds to answer C here. More positive, of course, means endothermic, more endothermic, or less favorable, right? We want things that lose electrons, not things that gain electrons.